Hello, everyone. This is lecture 17. I will conclude this discussion on filament stretching rheometry by showing you an interesting analogy between capillary rheometry and FSR. This is followed by drawing conclusions from these two methods. In particular, I will emphasize that if you want to have homogeneous melt extension, then it is impossible to reach steady flow state because of the tensile strength localization. For such localizations, I will show several movies to show the different characteristics in region 2, 3, and 4. In particular, I will emphasize the physics regarding region 4, where we see melt rupture. An untangled polymer melt ruptures as if it was cross-linked. So we think this is due to entanglement lockup, and we will use MD simulation to look into the detailed mechanisms leading to the entanglement lockup.
Let's have this. Today is probably one of the very few lectures where your great involvement is required. This is one of the few chances where your opinion matters with regard to the controversy that I started to share with you last time. And basically, there are two ways to examine the same sample. Okay? One is FSR, the other one is called SER. We had indicated that they give us report different results by construct, by default, if you like. However, that's fine. The question is, what do they mean, the different result? What do the different results mean? Right? So let's proceed with that. I, of course, want to right away. Oh Lord, this part. Yeah, okay, it is here. I of course want to right away reminding you once more. Besides this difference in instrumentation, our outlook, our perspective, looking at the response of extension is different. Let me remind you, this is the beauty of what I have done already. For the recording, I have summarized what each lecture was covering. So if you forgot what we said about in extension, what is the feature of yielding, it's discussed in lecture 11, starting at minute 22. So I have made this heading for all the lectures we had. So here's the contrast I want to make. I notice this is, oh, I see. So because it's not in a play mode. This is so inconvenient. I need to fix this computer. Basically, when I'm in play mode, it went there. It went to this screen. Jesus Christ. And it's interfering with us. Oops. So let me just get out of this. When you depend on technology, it's just so painful. I like to think it's equally painful. This is something I made a conclusion about. It's equally painful to be doing normal science. You are trapped in a paradigm. that you struggle and you cannot get out of it. When I say paradigm, a framework of scientific understanding that is assumed to be correct. And you are just enslaved there, and you just serve your masters there. Technology is worse. I mean, I cannot even call them my master. So in any case, let me borrow the, I still have something I can do. I can delete this and remind you the fundamentally different perspective we had. Go back to lecture 11 if you need it. Well, of course, not now anymore, but basically I tell you that, that we had a notion that if this thing start to show lack of further resistance to your deformation, that's when the sample is breaking apart. We call that yield. I motivated at least for half an hour over there, okay? So exactly half an hour. So that's a fundamentally different view. I just want to remind you that in a traditional view, this is how you plot the same data. Okay? Alex, are you okay? This is how you plot the data. You plot the true stress as a function of applied rate and call that transient viscosity or something. And look, there's no overshoot. There's no maximum. Why? Because I told you that when you have true stress, as long as your engineering stress does not decline as quickly as 1 over lambda, your true stress will still be growing. Yeah? So it's a matter of how much this declines. In any event, I feel guilty not to show you the tons of data that typically is represented in a different way than what I present. Okay? So this is how you do it, and typically, in fact, this was done with FSR, the one we just reviewed last lecture. So if you're not convinced, this is just another set of the same thing. Okay, always plotted as true stress divided by the rate, so you get some kind of transient viscosity and so on. And of course, you notice something peculiar already. First of all, if you like, you should already know that we talked about this. This is the zero rate envelope. So you have so-called strength hardening, quote unquote. And our interpretation that this goes up is because the sample has very difficult time, oh Lord, has a very difficult time yield, so that there is geometric condensation effect that causes the material to appear to be stronger. So this is again described previously. Just notice that this is their data, and for things that's using FSR, for things that people don't explain in the paper, look, instead of the maximum in engineering stress, their true stress start to show a maximum. Well, they ignore what that means. That's disastrous, sounds like. Sample is falling apart. In fact, people will simply take this point and say, oh, I have reached steady state. So I want to bring you back to the focus that using FSR, people claim to have steady state. Why? He says, gee, who bother? What do you mean by steady state? Who cares? Well, we care because they want to compare data with theory. The dashed lines are the theory. They want to compare with what theory is capable of calculating, which is so-called steady state. Okay? Let's move very slowly on this point. It's very sticky, as I told you. All the people who are ever concerned, either directly or I never can pronounce that word very well. Peripheral, basically. Even on the side, are concerned about this point and not clear about this point. So this point is what do we mean by being able to claim that you have steady state reached without encountering, oh Lord, I pray, gosh, this is just what I keep, without encountering any, if you like, filament breaking up, right? Which is what we observe. What do we mean we have that? Well, let's examine this a little bit more carefully, okay? Let's examine it by taking a look at what you see. So basically, after some point, it will strand like this. Okay, right? That's how this FSR will do. And they're monitoring the very middle. So let me establish a coordinate of z going down and 0 here. Then, obviously, you can claim, what you can claim is the following. You are watching this point, and that point, of course, at any moment has certain strand and has certain rate, and for which you have even certain stress. Other points, for example, here, you will have a different strand, a different rate, and a different stress. Yeah, for sure. Okay? What is monitored this comes back to haunt you, the same question. What you are able to do, or in fact, they are doing better than nothing. What they are able to do is to report the results as z equals 0 at the middle. Oh, Lord. And what they were able to do is to report the rate at the middle. Yeah? And then they could report a transient viscosity like that. Okay? This is the information they are reporting. Yes? Well, I think we did it here once before. Filament stretching rheometry. Yeah. So it's that device, the 2 disks. Yeah. Okay. So obviously, did I write it here? I write it here. Let me give you a few things by using a different page. Okay. So obviously, you got a. Be patient with me. You got your disk. Bottom is fixed. You're moving the upper one. This is your L. Okay. And obviously, at any moment, your nominal strand is nothing but L over L0, which is, of course, by definition, epsilon nominal. And that nominal strand, of course, is different than the strand at the middle. Right? How different? This page shows how different it is. I may want to use a different symbol of it. This is the nominal. Oops, sorry. Let's use that now. This is, in the book, I call it Z. I don't know why. But basically, this is the nominal strength. And this is the strand at the middle. Okay? So what happens? What happens is, let's describe it last time. Because your sample have the tendency to undergo disentanglement in some localized manner, with a tendency of wanting to break in the middle. The system compensates for that so that even though your nominal strength is not very high, the strength in the middle is already very high. Okay? Conversely, the strand away from the middle is lower, right? Because you just have an average that gives you the nominal strength. So I want you to pay attention to the following, which is rarely directly admitted in some more explicit way. That is, this is not homogeneous deformation. This is I call it textbook. This is textbook definition of uniaxial extension. That's all I learned from textbooks. I don't know anything different. This FSR is not. It is reporting an extreme amount of stretching in the middle, and the strengths are everywhere different. And it's not homogeneously stretched. So I think the first thing to acknowledge is this one is trying to manage to do it at a constant rate until it breaks homogeneously. And this one is obviously not applying a constant rate everywhere. And how you applying it? We don't even know how you apply it. It's up to the material's response. For example, if the material has a greater tendency to break, this curve could go even down further, don't you think? Okay? Because I'm just monitoring the middle. Okay? So this curve becomes somewhat arbitrary depending on your material. This curve, in some sense, represents nothing different than what I showed you here. It represents the information of this. That there is a distribution of different strands as you move away from the middle. Yeah? And how it does it? It depends on your constitutive property. Meaning, it varies from one sample to another because as you change your sample, you change it to a different polymer from A to B, you're changing the response because it's a different polymer with a different constitutive relationship. Okay? So this is a very confusing point. But let me bring this home, which I'm quite proud of being able to do. I think I'm not doing very much beyond what is in the book, but it came out during the writing of the book. I think what's remarkable, because I had such a big complaint about FSR, so I thought, gee, at least I should give the reader the best chance to appreciate what it is and what it is not. And therefore, I'm turning to the appendix of that chapter 11. I'm offering you a second look of capillary rheology. if you recall what we did with capillary, is if you have Newtonian fluid, then everything is very simple in the sense that what comes out per unit volume is exactly given by this. It's in whatever equation, whatever in the book. We went through it before. Okay? However, as you know, the wall stress is always related to the pressure, like so, independent of the constitutive properties. It's always true. However, if you really want to know what is the deformation field, you won't be able to know it unless you know the constitutive relationship. And this is why we were able to solve it for a case of Newtonian fluid, because we know the constitutive relationship. Otherwise, it's unknown. Of course, in general, you may say, hey, it may look somewhat parabolic-like, but we don't know the exact shape of it. Okay? Now, I want to inject one comment about the mission of rheology, which I'm just repeating, actually. The mission of rheology, as you know, is to study the deformation of materials. And classically or conventionally, this is done in two ways. This is done in just one way, but basically you need to specify the strength field. And the way we have traditionally do it is this is already prescribed a priori. Okay? It's prescribed a priori. In other words, as far as a student myself is learning rheology ever for 30 years, is, oh, the rheology is very simple because you have a rheometer already, which already prescribed the deformation field, such as simple shear. All you need to worry about is the stress response. And conversely, you can do in the stress mode, put the stress, and you assume homogeneous deformation, then you know what is the strength field. So this is how we do it. We prescribe, we assume the deformation field is possible to implement, okay? It's possible for you to dictate, to demand your material have certain deformation field. If that's the way to do rheology, two things. One is it's very convenient because this is already prescribed, you only need to do this. And second is, if this is not true, then we're in trouble. That's why we were in trouble when we saw shear bending. Because when you have shear bending, it means your strength field was not prescribed a priori, meaning before you do it, you don't know. Okay? So whatever we speak about is violating the traditional rheology in several ways. First of all, we discover typically we cannot prescribe necessarily a strength field. But if you insist on the classical way of approaching rheology, then capillary geometry is, of course, not in agreement with the conventional practice. Because capillary geometry, as I indicated, cannot prescribe the strength field, such as the velocity field. So it's a bad rheometer, capillary. Okay? Just keep in mind, it's a bad rheometer. By definition, because you cannot tell what is the strength field inside. Yet, the reason you cannot is because you don't know the constitutive relationship. Yet, constitutive relationship is what you want to know. So you see this logical, insolvable case. Okay? The analogy between them is tremendous. There are two parts that are amazingly different. One is the capillary, if you like, will also have a shear rate that vary as you move away from the center, with R being the variable because it's a cylindrical symmetry. Look at the analogy. So the shear rate is not constant. Your strain rate in this filament stretching geometry is also not constant. So there are two things that are similar, and also both violate what we practice with rheology, conventional rheology. You have not prescribed the deformation field. You are unable to prescribe that. Secondly, you are unable to prescribe a fixed rate of deformation. Okay? Thirdly, which is related to the next point I'm going to make, that like capillary, same as here, the stress is not prescribed to be constant in space. Three things. Now come back to a little bit of appreciation. Again, with shear as a remarkable control and example. Let's do something very clever. Because we do particle tracking velocimetry, right? Let me put particle in my sample. Let me measure the strength field. I know you say, oh, if you have a capillary circular, yeah, maybe a little bit hard to do. Well, let me tell you, you don't have to use capillary. You can use so-called slit die. You get the same story, that this field will be parabolic-like. And you can shine the light, you can have your camera looking into the screen and measure the deformation field everywhere. In particular, you will be able to measure, I claim, if you do it, to measure the stress at the wall. Sorry, the shear rate at the wall. Okay? So I can use a PTV to measure the shear rate at the wall. And I also already, by definition, know the shear stress at the wall, if I know the pressure. And I'm going to ignore the fact that there is entry effect, which we talked about. Let's assume the die is very, very long. There is no entry effect. Then we achieved what? We achieved two things. I want to make a comment. I know I'm verbalizing it, but since it's recorded, you can always dig all these words out from the recording. First, I make a side comment first. If you look at chapter 7 on yielding startup shear, as well as chapter 9 on the shear bending from startup shear, you probably by now noticed we've emphasized a great deal about the transient response. From t equals 0, how it responds and where shear bending occurs or not, rather than the steady state, which is a boring final parameter, final property. Why that is? Why you want to focus only on the transient? My claim is, even in processing, you hardly ever deal with steady state. It is the transient that's important. For capillary, I omitted a big part of it. In chapter 10, we talked about transient of the capillary. We omitted most of it. But it's in there. We just, for lack of time, we're not going through it. I'm just trying to indicate to you, even a capillary rheometry, largely it's a transient because the material is starting by coming into the die. The die was never long enough to finish reaching steady state. I say this because at least I want to indicate the capillary most of the time is only useful for thinking about steady state. So that's another bad thing about capillary not being a good rheometer, because you want to know the transient. To know the transient is a little bit complicated. I did discuss that in chapter 10. So in any case, you'll get a steady state, you get some kind of curve, whatever you have. So I claim the following, that if you give me capillary for any material, if I can put in particle tracking velocimetry to observe the shear rate at the wall, then at least at that point, right, at the wall, I will have a set of data available to me. Okay, right? At any of that material at that wall, I will have a very precise information about the relation between them, which is called flow curve. Such a thing is called flow curve. Okay? Now, here comes the million-dollar question. Okay, you labor to do all this, get this flow curve. Can you say anything based on such information about whether shear bending occurs or not in your material? Can you? Or you may even flip the question. You could say, oh, since you have PTV available, does PTV apply to capillary allow you to speak something about shear bending? Don't be confused with our observation of die entry, where we have shear strength localization. I'm not talking about that. I'm talking about in the die land. Yeah? This is all called, if there is a terminology, it's called die land. Entry is far there that we're not going to be concerned about. So can you apply your particle tracking and observe some physics with regard to shear bending? Shear bending, simple shear. Can you? Let me give you a formula, then you know whether you can or cannot. This is the stress field, shear stress in capillary. What does this mean? As I move across onion, right? As I move across different thickness, what does this mean? Looking into the die. The stress is not constant. Remember, the problem that we're dealing with shear bending is indeed we can confidently say that we have constant stress across the gap, yet it's shear bend. Right? So, number one, we have different interpretations about how to read the data, this versus this, that we see yielding and they don't. Number two, this rheometry, again, is offering us information just at one point, the very middle. Just like the capillary, one point at the wall. So I see many very basic differences, and at the end of the day, it all boils down to the following. That I keep saying this in general. I mean, in science, one can always come up with some protocol and then start to have numbers, such as this. You do have a number. You do have a protocol to follow. The question is its implication of what you observe and what can it help you about. Since it can never manage to claim that the strand field is uniform, that the strand rate is constantly applied to my sample, it of course can never answer the question of if I do apply a constant strand field to my sample, amazing, whether something else happens. So I'm just having a very modest objective, which is that FSR is unable to reveal the physics or the phenomena that you would observe under the condition of homogeneous extension at a constant Hanke rate. It cannot do that. It instead, by enslaving the sample, by asking the sample, hey, I'm going to shear fast, bye-bye, you guys can shear. Did I say shear? I can extend fast, you guys accommodate me, do it slowly, okay? I'm going fast. That's the FSR. So if you like, it is artificially creating a shear bending, if you like. So you better understand the contrast, right? Or contrast analogy, rather. That what we speak about in terms of sample breaking apart, okay, is the same as shear bending, right? The sample become non-uniformly deforming. FSR suppresses that because it's inherently allowing that to occur. The trouble is not so much of all that. The trouble is really to claim that you have steady state. Can you, let me maybe ask your opinion. I mean, especially you guys who have rheology. What on earth can you claim that you have steady state here? Textbook definition-wise. I mean, you got a sample in the very middle that claim to be in steady state, but it's feedback by time varying, undetermined. In other words, you have basically, don't you? You have basically indeterminate boundary conditions. I mean, look, folks, we present this view to the guys practice with FSR. To know a view, meaning without any success in terms of reaching an agreement, what this is, what is this is not. So if you allow yourself to define your state for just one plane, which is what they prefer to think that you can, they just go with that. Any comments? I'm really asking for help in some sense. Yeah. Well, that's good. That's good news. If you can't, I succeeded. I'm half joking. Right. It's actually up to you to tell me what I'm talking about. Well, obviously you see two different worlds, right? Two different scenarios. You know the word scenario, two different situations, yeah? We have two different situations, and we're trying to figure out what situation is doing what, right? And the question is, like today is, I voted yesterday. You guys, have you? I voted. It's like you vote. Which one you want to vote for? So you have two scenarios. One claim to forget about steady state if you maintain the classical textbook definition of what it is, homogeneous deformation at a constant rate. Then you claim there is no steady state. Sample break apart because it necessarily reached the physics of disentanglement. The other side says, oh, I never observed that. I stretched forever and it was fine. The data here is pretty ugly, actually. It's not very fine. What point make you think this is steady state? Okay? But they need steady state because they want to compare with theory that talk about steady state. So what part is not clear? In other words, we are facing enormous issue here. Enormous. In fact, issues that you have never heard until this moment, if you like. If that, by the way, if that strength hardening discussion was not impressive enough, where I talked about the fact that shear is a case where the loaded area is a constant, whereas in the extension, this loaded area keeps shrinking. Okay? That was causing the confusion about shear, about strength hardening. If that was not a big enough confusion, what about this? Can you make some choices? Can you help me? Meaning what the, because you're not brainwashed. You heard it for the first time. This is the best. Look, I don't pretend to say that this is uncomplicated. Okay? In other words, it requires you to absorb and digest and follow what I have described so far. And your question really is, what do you want me to say? That's your question. If I give you both apparatus, which one you would choose to do what and why? That's my question. No, that's why I'm slowing down in the sense we can take whatever time that's necessary today, because we have never confronted something more complex than this. Yeah. It's about. Look. Not really. Not really. Certainly, fiber spinning, film blowing, it all involves a significant extension. Nothing shear. Steady state, forget about it. Nothing reaches steady state in practice. Yeah, is that what you're saying though? In practice, in extension, we hardly can deal, we are hardly ever dealing with steady state. Is that what you're asking? Alex, so that's a good point. This is why I keep saying what I have said, that the reason folks desire to use FSR to do anything is, in fact, the other way around. They actually quite satisfyingly telling you, look, I can reach steady state that your other rheometer cannot. And once I can reach steady state, I can compare with my theory. There's more to come. I will. No, it's not. It's not. What do you mean definition issues? No. They claim to have reached steady state. So my first point with you is, do you agree it has witnessed steady state in the textbook sense of applying uniform extension at a constant rate? Did they? Did they apply constant rate and uniform extension? They don't. So the first thing as an author is I should say I don't. And secondly, one can still ask, under the scenario of having a ever-changing geometry, what does steady state means? Meaning, should I compare my data with theory? By the way, the theory, of course, assumes homogeneous extension, uniform with a constant rate. So should I compare? This is just a prelude. There will be a final discussion at some point about how this conclusion using FSR has further caused the workers in the field to be very confused much later. Here I'm just sort of, trying to get you input about, at least operationally, I think my point is as simple as I indicated, that there are two universes. One is data according to FSR, the other one is according to SER. They seem to be incompatible with each other. And my question was, can you help me resolve it? In fact, in some sense. You know, the dramatic point is this. Imagine FSR is the only thing we have ever done. By the way, that's not true, right? I showed you Ranegradov. Russian people have reported, where is it? This 4-zone breaking all the time. That's Ingstrom. So that's the same as the non-FSR kind. But imagine this is all doesn't exist. Only FSR exists. Then it seems to me we would have never heard about such physics as the filament will break up. Right? By definition. And that's pretty dramatic. The whole scenario, the whole phenomenology of the filament would break apart, would not exist. Are you with me? In other words, if the Russian didn't have the Ingstrom, they didn't have the rubber conveniently that they can stretch, and all we have is this disk, put our sample in between the disk and draw it. And draw it in the way they did. In other words, have a feedback loop. We would have never be aware that the filament would break apart. What? Not that at the end their filament doesn't break. I never have get a hold of such a rheometer. But if I go to their lab, at the end of their experiment, I would probably point it out, hey, what do you call the end of the story? right? What do you call that? He says, no, that's just steady state already. I don't have it. I'm answering for them. Isn't that remarkable? So this is the point. That's why the capillary analogy is similarly amazing, right? If you just rely on capillary, you will never have a day to know what shear bending means or how to observe it. It's the same. It's the same. Well, in shear, we know from day one. I mean, I learned as a student to rheology from day one that capillary is bad. It cannot determine it because rheometry is supposed to teach you constitutive relationship, but it turns out you cannot because the constitutive relationship, since the material put in, you don't know its constitutive relationship, then by definition you don't know the strength field, and therefore the capillary cannot produce enough information for you. And that's why, indeed, we go back to simple shear, where, watch what I just wrote here, right? Where the deformation field was thought to have been prescribed, that the experimentalists could control it. So it's just two legs. One of the, two pieces of information, we already assume one piece is available already. And that's where this thing is disturbing, the shear bending. Because it's very upsetting, because then it means, right? It means you cannot just dictate V, then you already know this. That's really upsetting. Because you hope that's the case, because that's the only way you can prescribe and proceed. But by now you should know very obviously that by the time you see shear bending, you could almost go back and say, oh, I predict that what Vinogradov observed should have happened. And that's exactly the case, that people have, of course, without building any surface instrument, it's in front of your eyes. You draw, it doesn't stay uniformly drawn. So I know in the book we talked about an equation where you can painstakingly, without particle tracking, infer what is the stress at the wall if you do several experiments. But the basic point is what I just indicated. Okay. Any questions? So this is just, I know this is a pretty hard part of the subject. I'm only paving the road for some further discussion in the future. So before we wrap up this chapter 11, there's one part quite instructive to discuss, okay? It's quite instructive, and that is this. Let's go back to this diagram. There is so-called regime 4. The only way to do justice is to take a look at this. In fact, it's long overdue. So remember, there's a regime 2, 3, and 4. Regime 1 is the boring capillary instability in the zero rate limit. So let me walk you through one of the phenomenology so that you have an impression. So this slide actually summarizes I hate to. I cannot use the play mode. So in any case, basically, this is the 4 zones, region 1, region 2, region 3, region 4, okay? So what's being plotted is just the failure mode as a function of the rate, okay? So I will be patiently going through this because this is the only time we do it and also the last time we do it. So the region 1 is uninteresting. So now we go to region 2. Basically, it's Weissenberg number larger than 1. Remember, I made a comment about communicating with the Russian guys, a Russian professor, about the different features in different parts. I got very confused because sometimes he says, oh, it really is rupture-like. Well, take a quick look. This is region 2. Using a piece of rubber is very convenient to do, wrapped around double drum. This is what the Russian people, actually, my colleague, Professor Malkin said, okay? This is very sharp, the breaking. Okay, not rupture-like, but it's very sharp. Yeah? It's pretty sharp, failed. And I made great effort trying to indicate what this is in the book that we're going to omit. And then in region 3, not in play mode, so you cannot see both at the same time. In region 3, the failure is extensive, real failure, meaning this unstable necking is quite extensive, like this, okay? So there is some elementary understanding about it. But when you go to region 4, where you stretch even faster, remember, faster or not, it's just a matter of Wi, right? So here, I switch to a different material, which is a material with a higher tau. So that the Wi is much larger, even though my stretching is now high. Not necessarily higher. Look at this one. Okay? What do you see as being different? What is different here? Because this is the region I plan to talk about now. What's different? There's nothing, yeah. It breaks very sharply like a glass. Or you can, it's not wrong to call that breaking brittle-like, as if it's cross-linked, but it's not. So this phenomenon, we see it probably for, by now, 10 years at least, ourselves. And of course, Vinogradov's group reported ever since the 70s. But this region 4 is not only most remarkable, but also is the one that I have the least understanding of it. We were struggling it, and I was not able to offer any more concrete understanding in the book. But they keep bothering us, and we keep wanting to know more, and now we do know more. So I want to share that part with you, to update the book, so to speak. Let me say something more elementary first about it. We will say quite a bit about tube model in the future. In other words, the dominant theoretical framework for understanding nonlinear polymer rheology in the near future. Yeah, we'll say something in somewhat detail. I just want to indicate that model cannot deal with this feature at all. For many reasons. I mean, we'll take a look at that model and take a look at how it's constructed. But here it's obvious. The language we use was not wrong. We just don't know how to describe it more appropriately. It is clear in this region 4, which is what the tube model cannot deal with. It cannot deal with region 3 either, or region 2. But in the case of region 4, it was very clear. the reason for that is the two models cannot really say very much about chain disentanglement. That's my brief statement. We'll go into much more details. I'm sure my statement here could irritate people, but I think upon further clarification, explanation, I'm sure it will become more clear. So what's clear in region 4 is what we call entanglement locked up. Okay? Instead of disentanglement, which I casually told you that it means this was entangled and then eventually slide out of each other. That's called disentanglement. Clearly in region 4, when the rate was high enough, that process, that mechanism is turned off. It doesn't exist. It locked up. And you can further claim, just based on this, that this indeed looks like as if it's cross-linked. Therefore, you can further claim that this could only eventually happen by being triggered by chain scission. The chain has to break. Okay? In other words, the sample cannot escape, or the system can only escape further extension is for chain to break. So the chain has to lock up. And how that happens, how could this happen? How this could happen, that's not clear. So I'm updating this book and talk a little bit about this region 4. And in the book, it will be the section of 3.3. I call it, basically it's basically about mel rupture, region 4. So we're basically, instead of this chain being able to slide, it does not do that. It locks up, and the chain tension can continue to build up. At least that much I can claim. And until conceivably chain scission occurs here. So how could that be in absence of cross-linking? Okay, so that's the real question. And you have to have some speculation when you wish to proceed, even if you have all the tools available to you. And the speculation, which may or may not be entirely correct, is that somehow this was the initial speculation, that somehow you form some knots between chains. Okay, just really not with each other. Okay, when you stretch further, the knots become tighter. So that's the speculation. And with that speculation, one can at least start to look for the mechanism. The mechanism for for the lockup of entanglement. So how could this entanglement locks up? Okay. And I won't be able to finish it, but we'll have a beginning of this. So a convenient place to do this, once you have some notion about what could be true, is to do a computer simulation, molecular dynamics simulation. So for anyone who, probably it's nothing unfamiliar to most of you, that in a simulation, of course, you have all the chains there, and in principle, you can examine every chain as you start to stretch this melt made of chains. Okay, so that's what we did in collaboration with Dr. Sigi's group. We had a student shared, and we subjected a bead spring model kind of chains. The chain lengths are 500 beads, and there are enough chains. So we did some stretching. And I can see that these slides are all unnecessary now. And I will just start by describing some features. So that's the beauty of simulation, right? You have access to all the information. So you have a lot of chains. The student labeled these are at least 5 or 6 different chains. 5 chains. So this is chain 6, chain 34, chain 124, chain 91. We have some reasons for choosing these different chains. Basically, you can get hold of one chain and watch and calculate. So what's being evaluated, for example, the blue is chain tension. Okay, so that's just this whole chain. You can see that it builds a lot of, so the force need to be read on this axis. Meanwhile, so this is just a chain, right? You know, they are connected by beads and bonds like this. Oops. Meanwhile, you can also try to indicate the orientation of the bond. So that's in the red. If it's near 1, that means they are all aligned in the stretching direction. So indeed, you find many of them are in the stretching direction. But look at this one, is a little bit peculiar. So you can see that most of the bonds are oriented in the perpendicular, in the direction of stretching, but there are a few peaks here, or valleys, meaning there are a few places where the bond is not oriented in the stretching direction. Okay? And similarly, you have the chain tension in blue. So that's some information that you can depict. It's not the end of the story, but basically you could you have the ability to look at. Let me give you this one particularly, to look at the chain 24. So this is chain 24. When you stretched by quite a bit, this is by the time you stretched, lambda already stretched 18 times. So the whole system is stretched 18 times. You can see that this chain has 2 places of hairpins formed by the presence of the other chain. See, that's one here, That's the other one there. These are straightforward. So to form this kind of junctions is what obviously expected because of uncrossability, and chains are sufficiently long. What is mysterious is why the chain doesn't slide around the junctions. So to answer that, you can at least see some complications of how chains interact. So you may not call this a knot, but you can see how complex they are interacting. So this silver chain is doing this. This dark, what is on your color, look like a dark yellow or dark green, is doing that. And then it also traps one of the green chains in the middle of that. And this is more complex with different geometry, different configurations. So that's a simpler case where you can see this essentially make a tiny loops between the two chains. So it turns out these kind of interactions might be the origins of the entanglement lockup. In other words, when you have chains stretched a lot, what prevents you from sliding is there are forces here holding it. Okay, so that's what you might be looking to find. And I think I will just be quick on this, telling you the most interesting part of the story. That's this. So what the student Yexing did was try to visualize why this particular chain, this particular chain builds so much chain tension. Okay, so it builds a lot of force in certain units that you would be able to appreciate. This could be reaching certainly could be reaching 50 piconewton, let's say. I don't have anything in front of me, or even 100 piconewton. And that's a tremendous amount of force. So the question is why it can build so much force, okay? It turns out this chain 124 is this chain that I described to you, this one that has two ends, two loops there. So what Yexing did was he calculated, so you have this chain, basically it's this chain. He calculated all the forces from other chains that's on this chain, that's acting on this chain, okay? Everywhere, he calculated everywhere. And he find, let me interpret this data, he basically find what I depicted here, with the arrow indicating the direction of the force from other chains, okay? This is a very remarkable picture. So what this is? It's a tug of war. So the chains are playing a game of tug of war. They grab on this end. They accumulate because you have more people on one end of the tug war. They just grab, contribute, add more and more. And unlike a normal tug war, this tug war involves two trees. So you have people grabbing this rope, and then there's a tree that's frictionless, and so the tug war can continue, as shown here. I guess I will pick up from this point on next time. And this is also unpublished result. But it gives us a lot of insight about how to treat entanglement. Okay. So for today, I think I will just stop here and wrap up from this point next time. Okay.